Yeah, thank you so much for the invitation. I'm not going to write on the board. I'm not a mathematician, but I admired the lecture this morning. It was really great. So I'll talk about sort of the intersection between big data and AI. I think, from a very different perspective than what you've heard, but hopefully we'll have some interesting conversations around it. And I want to talk really about sort of a journey of how we can work with data, from mining data to perhaps extracting insights from data to exploring principles and then using those principles and actually synthesizing something new or composing something new. Okay, and there's going to be a couple of different angles to this from my work, and maybe you can make connections to this, and we'll have a discussion on how this field is evolving. Sort of at the outset, I want to show here, this is something you've seen probably in different versions in the last years, with the advances in what we call artificial intelligence, which have to some extent been remarkable, but also have some really big shortcomings, as I'll discuss. Obviously we have benchmarks. Models have been sort of saturating these benchmarks, including in math. And again, I'm not a mathematician, so I let you judge how good that really is, but I can comment maybe on the scientific side of things a little bit later. But generally, I think other benchmarks, you can see sort of the advances here, right? So we had initial ChatGPT was all the way down here, and then within just a couple of years, we've seen a sort of exponential growth in this process. Now, this has been sort of within other contexts, of course. We had in 2016 some of the early reinforcement learning methods, which led to Go games being played very effectively. And we had recently, this is sort of 10 years later, this year we had some Math Olympiad winnings, I guess, by actually frontier models, without necessarily any kind of particular training on math, but they were just used to solve these problems. And I think my take on this is that what I want to talk about is really, these are impressive, but they're really important sort of open questions still in the creation of artificial intelligence, and especially in the scientific application, open problems. Okay, so I think these are, coding and math are really hard problems, but they're verifiable problems, and you can compute some reward and train models on this. I'm interested in scientific exploration. You don't necessarily have a truth. In fact, the whole point of science, of course, is to break sort of beliefs and establish new truths, new beliefs, and challenge existing paradigms. Okay, and so this makes this application, I think, very, very challenging. So this is sort of the context behind, sort of around which I want to present today, and share with you some of the work we've been doing. And I probably come from a very different direction than many of you, and I don't know why I was invited to speak here, but hopefully it's useful. Okay, so so my point, sort of making this a little bit more specifically, what we call AI or machine learning really is some sort of sophisticated form of curve fitting, right? We basically have data, and we can reproduce data from this distribution, and we can try to go outside, but a lot of times we fail. Okay, and that's sort of indicated here. And of course, in true discovery and having new knowledge creation, that's not going to be enough, right? We're going to want something like this, where we can actually go in between data and really try to figure out something new that we haven't seen. And these systems have to be built very differently, we posit, right, than the systems we're building today. As the systems today are sort of gigantic models, we're training them, and obviously they're closed in a sense. They're informed by some data, and they can never really go outside of the training distribution. That's, I think, something we all probably here in this room at least agree on. And so we're going to have to think differently about this. And this is what I'll talk about. And I want to also give a little background into my own connection. I know Tim Caxias, I think, is part of this center in some way or form, I think, right? So he and I share a little bit of history and sort of looking at multi-scale systems. I've been doing a lot of molecular dynamics simulations over the years. I try to understand how we can build, multi-scale models of materials and things like this. And one of the things we realized, of course, over the years is that you really can't brute force your way out of this. In fact, what we really got to do here is to build models that understand these cross-scale relationships, find these hidden laws or conservation principles that are, in these systems, sort of instead of simulating every atom by atom, we want to discover sort of the principles across scales. And I'll make this point a little bit further later. And this actually led us to, in 2010, into getting into, models or approaches like category theory, where we're trying to figure out, can we model systems differently, not just sort of in geometric space or multi-scale space, but actually in, functional relationships, and then also do meta-learning, trying to figure out how we can understand something like material and something like music or language, and make connections between them, right, and inform each other and synthesize information. This turns out to actually be quite important in some of the things we're doing now with multi-agent systems. Right? We can use some of those ideas from category theory and graph theory and actually build on this. So that's what I'll be discussing as well. And I was trying to talk a little bit about big data. Right? So I think this theme for this workshop is around big data, and I think there's obviously data in biology, like we've seen this morning. There's protein data, hundreds of thousands of sequences and structures. You have manufacturing data. You can have sensors everywhere. Weather, climate data. You have all these things, and what we see is that we really see a lot of limitation here, including in methods like, let's say, AlphaFold, which are very easily breakable. I mean, you can easily find a protein that whose structure is absolutely wrong. In my field, I work on silk, collagen, structural proteins. There's not a lot of data actually in the protein data bank, and so these models will totally fail very easily. Right? So you got to really think differently about this problem. And probably you have your own examples in your field. The other thing I'm really fascinated with is how do we create these artificially intelligent systems and create. And I don't have an answer to this, maybe, but maybe we have some ideas, right? Or at least some speculation. And then other data, of course, to give you a flavor of what we're doing in my lab. So we have, we're mainly a computational theory lab, but we also have some experimental facilities. We do some scanning of spiderweb structures. We do some scanning of, these sort of construction principles of how spiders make webs. And there's a lot of different ways, of course, by which you can collect data. So, fast forward now, I mean, the two things I want to think about or talk about is, again, sort of drilling a little bit deeper into the limitation of AI beyond the hype, right? So there's a lot of hype. AI can do anything. And I think there's really big challenges. Well, maybe not in this room here, but in the world outside, right? And I want to say there's two things that really are really missing, right? So examples, and talked about some of them already a little bit, but one is reduction. So really being able to say, here's a bunch of data, and I'm going to give you a scaling law, or I'm going to give you a principle that governs this data, and that can synthesize a lot of new things. And then the other one is sort of creativeness, creativity, where you might say, yeah, I want to create, structured novelty. In other words, you break the model of established ideas, right? So, and this is very important if you give a bunch of tasks to an AI system today. It will basically give you what you have trained it on, obviously, and you can't really do this kind of thing. So this is an old, classic example, right? So you create a new way of writing a symphony, Beethoven, right? So he said, well, I want to make it very long. I'm going to add a choir and, some solo vocalists in this. And it's like, maybe today is like, yeah, obviously this is how it looks like. But back then it was a revolutionary idea. It was sort of saying, this is totally crazy, right? And this is a creative input that humans have, right? That machines just don't have, right? And then so the question is, can we build machines that can do both of these things, right? And they're all both really important, and they can lead to one another. And I think these are some of the things we're thinking about in the group in my lab. And actually, one of my postdocs is here, Alivisa, who did some of the work I'm going to be showing today. So yeah, so what's at stake is I already talked about a little bit the sort of the real challenge I think we're trying to figure out in science for sure, and maybe in other areas. We want to think about creativity. We're going to talk about. I'm going to give you a couple of examples. Some scientific examples on proteins, but also some creative examples in music, and I'll show you how models can sort of learn on the fly. And that's one of the takeaways I think that we got to think about as a community is that, okay, we're not going to just train the model and let it sort of tell us something magical, but you have to build models that can interact with the world and improve their understanding, test hypotheses, and iterate through. And that really sort of is, of course, sort of this emergence of insight is something that we have to build machines to do. And that and it is very clear today how we do this. Right? So there's a lot of ideas around just training models and doing all sorts of fancy stuff like reinforcement and training, but they're all going to be basically closed systems that really have no ability to adapt unless we do something to them, and that's what I'll talk about a little bit. And then I'll give you sort of a personal sort of journey in this, the way I see this field evolving. The idea of using multiple agents has been around for a long time. Actually, in fact, since the 1950s and 60s, as you probably know. I mean, the term AI has been termed back then, and it didn't quite work. But I think some of the ideas that folks have sort of come up with then, and Mycin is an early AI system that didn't really work, but was, I think, very, very revolutionary, actually can be built today. So this is some of the things we can actually do today with some basic intelligence that's much more flexible and useful as a building block than pre-programmed, decision tree machines back in the 60s and 50s, right? So that's some of the things we see. And theoretically, I think we like to think, again, I don't know where. Yes, please.
I was wondering. It seems like probably for your talk, this distinction between generating truly new knowledge and interpolating is important.
Yeah.
So just to understand this better, like you said, it's kind of like likened to scientific advance as truly new knowledge. So to understand your distinction there better, like with transfer learning, or you can tell ChatGPT to say draw a computer, but in the style of Matisse, right? In some sense, a lot of scientific development often happens. Study what are good questions in cell biology, but study in the style of an economist.
Right.
Would that satisfy that in some sense interpolation, but also new knowledge?
Right. It's the incipient, step towards this. In this case, when you do something like transfer learning, you say you do something X, but use another principle. You are the other agent in the system that essentially tasks the model to do this, right? So you actually provide some really important data to the model, exactly. And so, and there's a great question. When we build multi-agent models, that's what happens. But it's not the human asking this or putting the sort of creative idea in there, but it's the machine doing this with agents, exactly. Yeah.
So
yeah.
You're saying basically it's interpolation when it's bad, it's invention when it's good.
Well, I mean, it's not bad. So in interpolation, it's not bad, but it doesn't lead to truly generative new compositional reasoning, right? Because you're going to be stuck with existing knowledge, right? And you might interpolate, but where you really want to go, and I have some plots later to show this. Let's say you're designing a new protein. You don't want to just design a protein that's sort of a combination of existing proteins. There's like an exponentially large or very big universe of proteins you can make. Can you make some proteins that have a totally new design principle? Can you discover that? Yeah.
If you can express it in words, is that already an interpolation?
If you can express it in words?
Yeah.
No, not necessarily. I mean, a protein sequence would be a great example for this. So we can write it down as a sequence, right? And there's a lot of different possibilities how you can synthesize that. Yeah. Yeah.
I should let you continue.
No, it's okay. No, it's great. I think the questions are good. I mean, I'll show you some things and maybe show some data you can see react to this a little bit, and we can talk more about some of those questions. Yeah. Okay. So I was going to say here to this. One of the things we think is important in building models. This is sort of taking a step back, right? So if you please.
Sorry,
yeah, of course.
Just one more point on that.
Yeah.
I don't really understand what the word create mean. So
the word
create. How do we know that humans create and machines don't create? So I don't understand what that means. For example, in the case of AlphaGo, you have this famous move 37, where humans were completely amazed by this. And I use the word create because it was completely out of distribution from whatever human did.
But AlphaFold was not was not a closed system.
AlphaGo.
AlphaGo. In AlphaFold is exactly right. Yeah.
It's not clear to me that humans create.
Yeah, well, that's a philosophical debate. You're great. I mean, I would say that
we are creating a distance.
Exactly. This is great. No, I love it. But I think the way I would define it, I'll show you some example in proteins. Right? You can actually, you can say, here's, the universe, all the proteins in an embedding space, and this is where they sit, right? And you can say, if you have, you ask a machine to make another protein, is it going to sit in this space, or is it going to sit like all the way over here? Can you do that? And I'm not saying, and humans might be able to do this too. It's just the problem might be too complex for humans to do. But yeah, if you do protein design, you can just see what's in nature and compare that. It's a lot more difficult in human creativity. So when we're saying, creating music and art, that's hard to measure. And so our framing actually, at least what I was trying to, during the talk here, is to talk about sort of these both things, right? Both of these things, and ask sort of questions, really from an experimental perspective. What if you were to take, a bunch of, sort of AI models that have not been trained on anything particular, and you organize them in a multi-agent system, and you give them the ability to learn. Can they, interact and organize into something meaningful, solving a problem? So that's something that we'll get to in a moment. So there's a couple other nuances to this. But yeah, I mean, measuring what's new, it's hard. We never know. I mean, what is ever new, right? I mean, but I would say there's certain definitions we can make in certain scientific areas for sure. Yeah. So what I was trying to show here is the sort of maybe for mathematicians it's very obvious, but for scientists and engineers, many us like to think about geometric spaces. We like to think about molecules and sequences and structures. And of course, this is not a very efficient way of organizing your models necessarily, because you want to maybe think about, okay, there's certain details that are really important mechanistically for, like in the talk you showed this morning, right? There are certain details in the way a protein is organized or maybe an organism lives, that makes sort of an outsized effect at a larger scale. So it's not necessarily averaging over scales and doing coarse graining and these kinds of things, but really building these sort of graph representations, which we, 10, 15 years ago started building out using, these graph-based category representations, which is a very elegant way, I think, of capturing the world. You understand, what are important relationships, what are the relationships you can ignore. Right? So you pay attention to the right things, like that pattern, you can group it together, you can coarse grain it, but there are other things you cannot coarse grain. And that's sort of the question that we're asking here. And I think this helps us in building some of the agents and actually, building models that can sort of relate things across different manifestations like proteins and music and sound. And when you have sort of a model of how, let's say, toughness emerges, or you have a model of how strength emerges, you have a certain relationship, you have a relational model. So it's not just you measure something and here's a structure, but you understand how the ingredients of that structure play together to form that outcome. And you can write it down, you can make a graph out of this, and you can then ask the question, do you see similar relationships, similar graph structures in totally different domains? Like here in these early papers, we looked at these analogies, between proteins and music, sound waves, and things like this. And then you can build functorial mappings. So you can say, well, how do you map this? And then what you can then do is you can say, well, if I have an understanding of something in one domain, and maybe this sort of graph extends in this domain, but it does not extend yet in the other domain, you can make discoveries. So this idea of sort of transfer learning is exactly this, where the human might say, oh, I understand how toughness works in silk and resilience, and here are the principles, can you help me figure out how to do this in a different system? Right? And then you have to, of course, create these functorial mappings. You have to figure out how do you replace the silk protein with maybe ceramic particles or metal particles or glues and interactions and so on. And sort of the human process of doing this was what we did with category theory back in 2010 or 11. And this actually, at that time, you could not have models do this for you. Right? Now you can, and this is one of the early, and I'll show you this later, some of the early agentic models we built used, you can use very simple language models, in fact, even to do this, and they can begin to ask these questions and do these translations. And that's exactly what you're asking. Right? So you can give this kind of problem, to a language model, and the right framing allows the model to help you answer the question, right? And if you can have a machine pose the question, then you have an automated discovery, essentially. So this is pretty much all I wanted to talk about. No, I'm just kidding. But it is a very important part of what I wanted to convey. Yeah, yes.
Like, what's the input that goes into the system? Like, what do you ask it to do? How do you?
Yeah, I'll show you. I'll show more details. I mean, this was this was a pen and paper, right, on using category theory to sort of, write down mathematical. This is David Spivak. Some of you might know him. He was at MIT at the time who worked on this, and so we worked on proving analogies between very different systems and trying to understand their relationships using category theory. So it was entirely human driven, and we wanted to show that. But I'll show you later on, of course, in the modeling, sort of what comes in. Yeah, so I think, typically this is actually a great plot for this to show this. So if you're, one of the, the things you see in building sort of generative models that either reduce or synthesize is that you put in usually some data. And the data could be, in the most extreme case, it's just information, right? So unconnected facts, and then the model will figure out relationships, right? So you say, here's a bunch of measurements of amino acids, and here's a bunch of properties, right? And so these will be points, and there's not necessarily a connection. There might be a connection between some of those things, but not really mechanistically across. And when you build, essentially simple graph-based transformer models, they will make these connections, right? So they will say, I need to understand how to make predictions, and so I will build a graph between every input token or an input component, and it will create a graph like this, and then it will hopefully make a prediction that's useful. It will be closed. So in other words, again, this is a sort of baseline, right? So even if you train it on all the books in the world, it will learn how to maybe approximate the books, right? But it won't create anything new, because in fact, if you train it on, let's say, basic fine-tuning, the models will basically produce the most likely way all the books are written, or the most likely paintings, or the most likely music made, and it sounds more like a sort of a distribution. Now, if you push the system out of equilibrium, so coming back to your excellent question, right, you say, hey, I don't want you to make a painting that looks like all the sort of canonical paintings. I want you to make a painting that has sort of interesting ingredients, or then you begin to push the system out of equilibrium, but you need another agent for this. Right? So now it's no longer just single AI. And that's sort of the interesting thing, that we have actually some baseline intelligence models with LLMs, essentially, or multimodal LLMs. And that doesn't mean just language. It could be sequences, it could be DNA. I mean, it could be. So when I say, I don't like the term LLM at all because of that. But it is a transformer model that takes a bunch of information, tokenizes, and builds graphs of it, right? So that's a better way, I think, to look at it. And then you have some baseline intelligence that actually you can work with, and they can talk to each other, they can communicate, and they can even autonomously negotiate solutions and find an equilibrium. So that's what I'll go into in more detail. Does it make sense? So this will be, I'm hopefully being interesting. I don't know how, I have no idea all your background, so maybe I'm telling you things you already know, or things you've already thought about many years ago, but yeah. Okay, so please keep the questions coming. And I don't know, I mean, this is just something maybe this, again, this audience is very informed, but I show this, I say, hey, people always say, yeah, AI is going to do science. And I say, well, all AI does is really this, right? So it memorizes. I mean, if we wouldn't teach AI Newton's laws, it wouldn't know it, at least today. I mean, it would basically be able to reproduce all these phenomena perfectly, but it wouldn't be able to predict what will happen on the moon, right? Because it doesn't understand some of the fundamental principles behind it. And that's a really important thing to know, I think, because a lot of this, AI right now, it's very impressive because you have something that is sort of maybe not a PhD, but almost like a very knowledgeable entity in different fields. And if you're not an expert in something, you'll be very impressed. I mean, I'm very impressed. But of course, if I ask an AI model something in my field, I'm not very impressed, because yeah, it will tell me everything I know. It's pretty cool, but it's not going to make a new discovery. In fact, you can feel the boundary, right? That limit. You can feel it. And so this is just to explain that. So we've got to really come to this, and we're not there yet. So no matter what we think, but it's a long way to go there.
Can I
Yes,
ask about
of course.
ethical debate?
That seems like actually quite unfair. Because like, of course it wouldn't know F equals MA, neither would we, unless we could do experiments.
That's right.
Here you're just talking about a computer system.
Yeah, exactly. Exactly.
So that's not really, right?
It is absolutely true.
Unless you have the AI running its own lab.
You're totally right. You're totally right. No, you know, that's, yeah, of course. Yeah.
Plenty of major theoretical advances were based on past experiments.
Yeah.
I mean, Einstein didn't do any experiments.
I was going to say that. Exactly. You read my mind. Exactly. Yeah. Well, exactly. So, right. So two things. Yes. Yeah.
Yeah.
Microsoft Word at that time wasn't precise. It was giving a result right in the middle. People were using Microsoft Word to contradict Einstein. If you were right, Microsoft Word.
Oh, really?
Yes.
Oh,
Well, so I don't know the history that well, but I mean, I think both is a good point. So first, I would say exactly there are certain theoretical reasonings we can do, and it is sort of the example I was going to give is that you have some observations, big data, right? We wouldn't call it big data back in the day, but and you're trying to make sense of it, and you're trying to say, well, there's all these different theories, but I'm going to go take a step back and create an abstraction that might explain all of these, and then, but you will need, of course, empirical evidence. So that's why I said in the beginning. Science is very different from any other system because it is never complete. You will hopefully the whole point of that is to falsify it or verify it and get evidence. So yeah, you ultimately will need to go and try to find the limits of that theory until you find or maybe find the theory of everything that explains everything in the world. But that we don't know, right? So, but yeah, exactly. So you will ultimately need theory, but there are principles I think we can extract from data. And it could be as simple, I mean, the modest things we've done to date would be, identifying scaling laws in protein folding, right? Things, and so the other point to this, and actually I'll show this later, it's not necessarily that we need experiments all the time. We can do simulation, we can simulate physics as well. And so when you think about systems, AI systems that can pose a question and create a hypothesis, they can say, well, can I find an analogy? So I'm walking you through how our models think. So they say, well, I have this idea how I might explain these phenomena. And, the model has the ability maybe to go back on the internet or maybe run a physics simulation and test this hypothesis. And the unique thing now, sort of maybe very different than just 2 or 3 years ago. 2 or 3 years ago, maybe AI could come up with a hypothesis and you would read it and you would have to do a lot of human intervention to actually run the simulation. Today, an AI model can in fact create a hypothesis, agents together. They can write a code to run the simulation, get the results, analyze the results, and decide on a new simulation. So Olivier's this is what he's been doing for the past few years in my lab. So this is possible. And of course, yeah, it's very incipient. I think one day, we'll look back, this is sort of very primitive, but it is now possible to have machines in silico for sure, do everything from writing code, running simulations, physics, reading the internet again. So you go away from, we're just training the model and getting some sort of mean average canonical representation to, I want to find these really unique features that might be, so the observations that if you think about an AI model or machine learning, it will kind of round the edges, right? Because that point is outliers will be smoothed out. That's where the innovation lies. So this model can go back and say, I have this idea, I have this model that I'm proposing, and I'm going to look for evidence if this thing that I'm thinking about actually might be there. And in fact, it might be there, right? So the previously trained model will not do this because it doesn't know about the single data point that might be the outlier, right? Which is the key to explaining this new theory. So this sort of, you get, I think, the way we think about problems. So this is sort of the principles by which we have to build these systems to really become, smart. I use superintelligent. Maybe that's a little bit too, hyperbole, but it is sort of what I mean by this. It is becoming. We want to build something that is more intelligent than humans. If the model is only as good as we are, it's great, and for engineering, it's actually quite useful. But for the scientific discourse and thinking about building machines that are really going to teach us something, that's not going to be enough, right? So anyway, I'll show you a lot more details, actually, of course, and some results, and then hopefully we'll discuss those also. But so here's some early attempts. So this was MySynth in the 1960s and 70s. So the idea is old. And it is very important, right? So a lot of this is people going to come out today and tell you, oh, we've made this amazing thing and it's just scaling stuff. Well, scaling is important, but it's not the answer to everything. I mean, obviously it cannot be and unless some major theorems are violated, I think. But this idea of using agents and this idea, essentially what people are building today has been around for a long time. It's just that in those days, the agents were not transformers or graph models. They were basically, hard-coded computer programs that have if and then statements in them, right? Fortran code or something. And they were so brittle that when you ran these systems, they worked for every single toy model, but they failed miserably as soon as they went, slightly different formatting. Obviously, they couldn't handle it. And then fast forward, so some of the models that we can build today, same idea, but now we're using transformer models. LLMs or vision LLMs or more complex models, but they are much more flexible. They're based on neural architectures, but they understand language and symbols, and they can build these relational graphs. And so now, even if your input is slightly different, the question is asked slightly differently, they can still understand it, right? So there's this, a quote by Jensen Huang, or I don't know if you've seen it. He gave a lecture once about the sort of development of AI, and he talked about how the magic of ChatGPT was that the computer sort of understands you. Have you heard that? He says, it's very, very intuitive. So before that, you program the computer, and it's hard. You have to write C code, Fortran code, and you have to make the computer get it. With ChatGPT, you can say, yeah, write me this algorithm, or like you said, right, write me this algorithm and throw in some ideas from this thing and that thing, and it will actually do it. It kind of understands you, right? So this is very different. So this is sort of what these models are doing, exactly. So these agents are all kind of, multimodal language models that can do all these different things. So, they're agents that write code, that execute code, search the internet, search databases for proteins, run a physics simulation, fold the protein, get a signal. Oh, does it actually look like this? So this is sort of, conceptually simple, but extremely powerful. And it's like taking, something you're sitting there, but instead of taking just one, model, you take a bunch of them and you let them talk to each other. And that's very powerful. And this creates a level of compositional reasoning that I think, we can actually trace back. We can say, okay, so how did this model come up with a new idea? And exactly like you were, sorry for pointing at you but you asked exactly the right question. So, this is sort of the model. So it's not like a human asking this, but the models each other will say, okay, I'm coming up with this new sequence idea, and I'm going to take a little bit of collagen, I'm going to take a little bit of silk, and yeah, to create stability or maybe create a linker, I'm going to need to use this particular sequence. So it reasons over the process, and it creates atomic concepts that it combines, and it puts it together, and it asks questions, and it builds a structure of thinking through the problem, right? And it then falsifies it, right? So the really, really key ingredient here is that the model, comes up with an idea, right? A compositional step, and then that's not the end. It goes back, and it says, now I'm going to fold this protein, and now I'm going to run an MD simulation. Well, if I run an MD simulation, I have a time limitation, right? So it's not the whole answer, but it's a signal. If my protein falls apart right away, or another protein design is more stable, that tells me that the one that is not falling apart right away in MD is probably the better choice. So it doesn't mean it's the best answer. There's no proof for that, but it means there's a signal. It tells me, well, this design is probably better than this design, right? And that's what the agents can negotiate pretty easily. And of course, you can sort of immediately see this answer is going to be a lot better than the answer from a single model where you say, decide me a protein. And you get a sequence, and then you have to do all the work. And most of the time, the sequences are nonsense, or they can't be made. They don't do the job. They're toxic. I mean, there's so many different things, right? So I have to go a little faster as we're going out of time. But so I'm going to show you examples now. And one other so we've done these agent systems, and then we've also become really interested in saying, well, so the agents basically are built on the idea that you say, I have agent A, B, C, D, 4, 8, whatever. One is a coding agent. You program it to be a coder. Basically, you take a model that's very good at coding. You have a retrieval agent. That's a model that's basically specialized to search the internet or find papers, right? And so you predetermine the roles, basically. So the other thing we've been thinking about recently is, what if you don't predetermine the roles? What if you say, I have sort of identical copies of, well, bees, not bees, but agents. Each of them would be at the level of maybe an O3 or 4. GPT-5 is actually one of the models we've used recently for this. Sort of the best model we have right now. And you have identical copies of them, and you let them evolve. So instead of deciding a priori what they're going to be, or what they're going to, how they're going to act, you let the system sort of find an equilibrium. And of course, it's a classic negotiation of an equilibrium because, to get to an objective, if it's a trivial objective, it might be a trivial solution, but if the objective usually is complicated, right? You want to make a protein that is an alpha helix. Well, of course, there's a solution maybe, but there might be other constraints, like it has to be soluble, it has to be non-toxic, it has to have maybe certain patterns in the sequence. I mean, you can come up with all sorts of complicated criteria where there's going to be competition. And so the agents have to figure out, it's not just one thing I want to maximize. There's a lot of different parts to getting the objective solution, and each agent has to act in the, of course, obviously in the interest of the final outcome, and not only in his own best interest. So in classic Nash equilibrium forming, right? And you can achieve this in a bunch of different ways. But this is what sort of the swarm idea is behind. So it's very interesting. So we'll talk about this later. And of course, there are examples in nature, from ants all the way to bees. Yeah, of course.
What's the fundamental advantage of having multiple agents? It's like when you assign tasks to them, I could understand them. But now you say just let it evolve. Is it just like a form of some kind of parallel processing, or?
Well, there are two things. One is one is a basic question, an experiment I'm trying to do, because so you can say, so the naive beginning of an agent would be, you predetermine the rules and you say, okay, you may be thinking, in my lab I have experts at ABCD, or in a university, I'm going to create these sort of, it's a very human-centric way of organizing this. But you can ask the question, and then of course you have to specialize the agents. You might have to train them. Agents have to be special generative agents. This is awesome because you have them. Maybe you can download them from, Hugging Face, and you can get a protein designer, and you hook it up with the MD model, a physics agent, and you connect it with a literature agent, and and this is what Prod Agents is. This is amazing. I mean, it does amazing things. But, I'm trying to say, well, what do we even need to do this? Can we just have, the best model we have has never been trained on proteins. In fact, it has knowledge about everything just a little bit. So it's canonical knowledge, right, about the world. Can that solve really complex problems? And so, in fact, it can, actually. And I think this is a shift in sort of, we're trying to show with these experiments, well, first of all, we're trying to show, can it be done? And if it can be done, could it be a new paradigm? Because there's a whole industry around us. I mean, there's thousands of companies built around training specialty models, like about proteins and drug design. Well, maybe the future doesn't need this because if you create a swarm of agents that are all the same, but they can figure out through rewards and penalties. There's a classic, so it becomes a reinforcement problem in a sense, right? If you can find an algorithm that will give the right rewards to find an equilibrium, and hopefully a good equilibrium, and that's where the innovation lies. You have a very different paradigm. So now you're no longer training the model, pre-training or post-training. You're actually training the swarm to behave in a certain way. So and I think that opens a whole new picture of possibilities, as we'll show later. So these, kind of, obviously not ants, but they can do things much more like humans. We can do a lot of different things. Like we can do, maybe talk about this. We can go, I don't know, build something. We can go to the beach and build a sandcastle. We can do all sorts of different things, right? But AIs cannot do this, right? So an AI model like AlphaFold can do nothing but fold a protein, and that is not even out of distribution. It fails, like I said, right? So very limited. This, well, yeah, these agents, if they're always the same, so I'll show you later. So these agents, starting from, let's say, GPT-5, which is currently one of the best models, they can design proteins. They can also compose music. It's exactly the same model. You just tell them different things to do. And you may adjust how they're getting rewards. So and even that they can do themselves. It's because if the agents have they can write a reward function. If you tell them, figure out, instead of just, if you want to have a protein design, you need to have something maybe to fold the protein. Okay, they have to provide an API call to AlphaFold, or some other feedback from physics. For music, maybe they look at the score, they have to find a library, and the agents can do this entirely on their own. Right now we're hand-holding them to do this, but this very soon they'll be able to do this on their own. And so now, sort of they start as, and they can even decide how many of them they need. And so you can see a lot of, kind of reverberance of these are the early ideas from the 1950s and 60s. And I emphasize this because this is not new, actually. It's been sort of hypothesized, believed, thought about for a long time. But the agents back in those days were not suitable for building anything like this because they could not write code. They could not sort of, create new instances of themselves with different flavors. But now we have reached sort of some baseline intelligence where you can actually begin to do this. So that's sort of where we are. So let me skip this. Let me skip this, and let me show you. Well, actually, so the inspiration for this came from MD, like molecular simulation, the kind of stuff we've done over the years. And this is a sort of trivial example, but it's sort of intuitive, I think. Yeah, so you take 1,000 particles, I think 1,024, but doesn't matter. I mean, 1,000 particles, and you just change their potential. And obviously, you're going to get very different structures. Right? So the question, and this comes back to your question a little bit, what you're asking about. So the design question or the training question becomes, okay, I have particles, they have a mass, maybe a volume or some space, I guess. Maybe not, actually. Let's say the mass is conserved because volume is a little bit related to the distance, I guess. But they have some innate properties, okay? And then you design the interactions to lead to a certain outcome. And the design problems, or what you optimize for, is this. So you say, I want to get this. And then what you need to figure out is how do the agents need to interact? So this interaction graph here, which is a very simple distance-based metric, is going to have to change to achieve a certain outcome. And your feedback, could be gradient. You do gradient descent of some sort, backpropagation, or you can use reward signals, RL techniques, and you don't need gradients for that. But you just you can do things more efficiently, or you can even do non-weight update in LMs. You could, in context learning, you can simply steer the behavior of models through giving it data during inference. So there's a bunch of different techniques to do this in practice, but that's the inspiration. And of course, this can be so we've tried this for the very first time actually in 23. And it's sort of, I think I walked through this a little bit already, but I'm going to walk one more time to show you how this went. So we had, so I came from the field of doing, MD simulations, maybe training force fields, and I would do this myself, or my students. And you had a new material, you would have to train it. You have to basically do some DFT, collect some data, fit some function, and then get a potential and things like this, right? So this was sort of what PhD students were used to do. Maybe a little more fancy, of course, but in general, right, this is what humans would do. They would drive this process. They would write the input file, pick the right DFT flavor, pick the right fitting function, validate everything. So the simple experiment we did in 23, this was right after, ChatGPT came out, and this was actually the GPT-4 model, which was a really big break beyond the original GPT 3.5, which was originally ChatGPT. And with that, it didn't work. If you were to say, so the idea here was basically, you put a bunch of agents together, each have a role. One is writing code, one is executing code, and then maybe agents that can read the internet and things like this. And yeah, if you had GPT 3.5, and you can try this, it wouldn't work because the agents would like to talk to each other, but the code wouldn't work. They wouldn't be able to fix the code. They would be almost like the Mycin model experiment in the 1960s. It would just be very brittle. But GPT-4 was almost as magical. It's like this emergence of capabilities. It wasn't perfect, but it was far better. And what this could do, so you would ask the question, kind of like this question here. And this was a language model. So this was not a machine learning potential or anything like this. But it basically said, so, okay, I don't know the answer to this question. I don't know the energy landscape of this molecule. But I do know how to get the answer, potentially, by writing code to write an input file and run DFT and get a bunch of different data points. And then I collect these data points, I fit a function to it, and then I can answer the question. So this is a very, very simple example here, but it shows a very different workflow, right? So any machine learning model, and come back to the early picture I showed with the distributions, it will be very confidently telling you this is the answer, right? If you take a graph neural network machine learning potential, you give it a new molecule or something new, it will give you an answer. It's going to be wrong, but it will tell you it's correct, right? So these agents were able to say, I don't know the answer. This is very, very hard for the model to do, but I know how to get the answer potentially. I can do this DFT. And again, it doesn't mean it's correct. You know, you could be validation steps, but it's much more valid, of course, you know, than any other technique where you just memorize. Right? So it doesn't memorize, it begins to create structure. And that's the basis actually, yeah, the basis to a lot of the stuff we've been doing since then. We've built real models. I mean, this was a toy problem and we've done flavors of this, but the point of this is really, yeah, that you don't sort of the model, the agents begin to have an awareness of what they know, what they don't, and they have some ability to generate new data on the fly. And that might seem, it's actually very obvious, but it's not how most machine learning works, right? You train the model and you hope something amazing happens and every answer can be derived from this. And that's not true, I think. And you can prove it actually with many, many examples, I mean, theoretically and also empirically. So this was different because the model would generate its own data and then answer the question, right? And based on this, we've built a whole bunch of different models like this. So we've built this for protein design, what Alevisa has done. We built it for mechanics problems. And you know, the beauty of this is, I think, that if you have tools, let's say in this particular, this is prod agents, we had a bunch of protein design tools, some of our own, some existing models. We had, you can hard read, but it's a physics simulator like NMD engine, like NAMD or LAMPS. We had, you know, yeah, folding tools, Chroma, Omega Fold. It's like AlphaFold, but faster. And so if you're designing a protein now, you can do a couple of interesting things. The model can come up with a new sequence, but it can also test the sequence. It can say, yeah, I'm going to build a model of it. I'm going to run an MD simulation, as I mentioned earlier. And I can even go back to the literature and say, is it actually novel? Or has anyone ever talked about this sequence, right? So all of these things can be done by the agents. The question is, you know, can the agents do this autonomously? And the answer is yes, well, they can, right? So it's not, it needs improvement. And, you know, the GPT-4 model used for these kind of things was very simple. Now we have, you know, 1 or 3, we have GPT-5. I'm really talking about frontier models. The idea is really, yeah, standard off-the-shelf models, you put them together in a team, they can do really amazing things. And every advance you have in these models is going to multiply because they interact, right? So we've done systems like these, and then the thing that happens is that, of course, you can pre-program how these agents interact, but you can also let them decide on their own. So you can have what we call a planning agent. So it would be an agent that says, here's a question, and this agent is sort of the agent that understands all the different tools available, all the different agents and their roles, and it will decide how we're going to try to solve this problem. So it will say, okay, first, it's the planner, you know, I need to have maybe use some tools, collect some data, make a hypothesis, run some simulation, and then I'm going to use the critic to critique the results, and it will make figures. It will make a table, JSON, or whatever data format, and it will try to reason over this. And it says, oh, here's what I believed. Yes, please.
Imagine you have to give the planners constraints. Do you let it do whatever?
Yes.
How do you implement that?
Yeah, no, it's a good question. I think we have to give the planner knows, you know, one constraint is it has certain tools. And you can tell the planner, you can only use those tools. Okay. However, and it's a great question. So if you tell the planner, you have all these tools, but I also have a coding agent and an execution agent. So you can write any code you want. That can also be done. And so now, you know, the universe of possibilities becomes even bigger. And so, yeah, you have to constrain it, absolutely. And Alevisa, I can tell you, you know, very quickly, if you give them no constraints, yeah, the compute becomes sort of exponentially larger, yeah. But it is actually an interesting point, you know, when you, so like all these, so these models here, right, you know, they're existing machine learning models maybe, that basically are surrogate models, are predetermined, or maybe a physics engine. But if the planner sees that the best solution to the problem isn't necessarily in these tools, but it has, again, a tool to write code and execute code, it can do that too. And what happens then is that it will simply write code. And it might write a code to train a surrogate model, to then use the surrogate model to quickly iterate through designs and then test them. It is totally mind-blowing. So the whole thing now becomes, you know, all these things that we're really, I mean, I guess I sort of said, you know, there's labs and companies built around the idea of training models. It can be totally automated. I mean, and you can see this when if you've used, Cursor or maybe a Claude Code, right? You can tell a Claude Code, I want to make a transformer model with so many layers, or even figure out the number of layers. But here's my data set loaded from Hugging Face. Here's my my key, my API key. It will do everything for you. It will download everything, and it will error correct. So that's the other big thing, right? So when you think about a model writing a really complex code and executing it, this doesn't have to work the first time. And in fact, in our early experiments, it's the same thing. This did not work first time. The DFT code didn't run the very first time, but it read the error message and figured out how to fix it. So it can do really quite incredibly complex things, and that are beyond the tool set. But yeah, I mean, usually we want to it's a good idea to confine it. Otherwise, you get. But that's where if you have enough tokens, enough time, so this becomes limited by, I mean, let's say tokens is not an issue. Let's say you have infinite resources, but it really becomes a limitation of how quickly can you run these really big frontier models that can do all these things. And they have a certain time scale. Even if you use OpenAI APIs, they just take so long to do their work. And so that's the limiting factor. But if that can be sped up, you can do these things much, much faster. Yeah. I hope that makes sense, yeah. So you can do with this, so again, sort of the outcome of this might be, you might say, yeah, design me a protein with certain objectives, and you can give it numerical objectives. You can say, give me 80% alpha helix, 20% beta sheet, or you can give an actual, natural language description. It's either way is fine. That's the beauty. Or you can say, use this motif in your solution, like this amino acid motif, but make it all alpha helical. And you give these really tough objectives, which could be make something that's alpha helix, but you're using a motif that tends to form beta sheets. And this is where the kind of competing dynamic equilibrium comes in, because the agents can't cheat. They can't just make the obvious solution because it's a negotiated solution between the competing objectives. But you can formulate it very easily in the global objective, and it can be tested. Right? So it's not just predicting it. There's physics evidence for this. So I think it's better. It's better than just a single model, and it can be done for other things. So we've done it for alloys, metals. But at least I can talk about this. So this can be done in many different fields. It can be done even further. I mean, so we've tried this more recent work. It's a model we call Sparks. Well, we didn't just solve. So here, the objective was design a protein, right? And it can do a pretty good job in what we want. But we can also do it a little bit differently. We can say, instead of giving me an answer to a question like that, can you give me sort of very generalizable insights? And so now the agents are tasked, essentially programmed to develop not just an answer, but develop principles to an answer. And largely done through prompting. I mean, you basically give them a different objective, and we have a construction principle involved here, where every agent has sort of an adversarial counter agent. Right? So every agent has a creator of an idea and also a critic of the idea. And when you pair them like this, you can generate sort of a hierarchy of agentic interactions, and you can make them produce repeated hypotheses. And so the way you do this is you don't let them just give you an answer to a problem, but you say, I want you to really find the weaknesses, like kind of we talked about earlier. So I want you to come up with this new scaling law that might explain how certain patterns of amino acids lead to a certain outcome. But I want you to find the weaknesses in there. So the counter agents or the adversary agents, that job is basically to drill holes, right? And so they will ask questions. What if this happens? What if that happens? Are you really sure? Well, try this sequence. And so this can be run for a long, long time. So you can repeat and do this. And ultimately, you'll end up, come to this at results like these. So this is from the paper, and it's all in archive if you want to take a look at this. We get things like scaling laws, and we're very excited about this because all AI before, obviously it's designing things is great, but this leads us into something like understanding. So you can begin to see the machine can tell us, here's a sort of these are two different mechanisms that the machine came up with that control the force of this protein, the stability of the protein. And it's a lot more human-like scientific insight than just saying, here's a protein that meets this particular demand. But it says, this is how you get there, but these are the mechanisms that get you there. Here's a scaling law or competing effect. Sorry, yes?
Time to wrap up.
Yes, oh, I'm sorry, yes, of course, yeah. So let me just show you, so I'll skip over a bunch of these things. I will just show you something on the swarms, right? So this, I'll skip this. It's a 4-player game, but I'll show you something on swarms. So the idea, and I'll be doing this in like 2 or 3 minutes or so, we'll be done. One on protein, one on music. So we talked about earlier, right? So we have now said we have all these predetermined roles, like adversarial agents, pre-programming them. What if you don't want that? What if you had just sort of a bunch of agents that are all the same? Let me skip. So here's the example. And each agent might be responsible for something in the design process. It could be spatial. So it can say each agent is responsible for one amino acid, or in music, one note or one bar. And they're all the same in the beginning, but they have a history, they have a memory, they can adapt. Right? So they learn from their actions. Of course, in the beginning, if you give them an objective, they're not going to know what to do at all. They have some baseline understanding of what they're supposed to do, but they don't really know how to solve the problem. But as they go through iterations, they talk to each other, and they become different. So the swarm of agent, which began the same, adapts, and it repeats, and it works. And so it has a differentiation at the end. And to come sort of to the punchline, I know we're without time, they can solve de novo design problems as good and better than the frontier protein design models. And so this is really, really significant because there's a whole industry quotation mark of models, right? I mean, this is, here you can see this. So this is the sort of state-of-the-art protein design model, protein MPNN. And that's been trained with huge efforts on proteins, right? And our model, and you can kind of see this is the space of known proteins, and this is sort of where these models are trying to go. Our swarm can make proteins that look like the ones this model can make, but it can make a lot more diversity. It can make proteins that are totally different. And again, no specialization. So this same model, so now this is the end, can also make music, right? So the swarm, instead of telling the swarm, make a protein and getting rewards about that, the swarm will then say, yeah, I want to compose music. And it can do, so it's the same architecture. A little bit different in the sense that here we give every swarm component 1 bar of music to compose. They, in fact, sort of the most interesting part actually is a swarm design where the agents never see the global objective. So we have different implementations of this. This guy here is we call traditional multi-agent swarm. There's an agent swarm, and they have some sort of feedback from a global perspective. There's a global critic, like in the protein case, that sees the whole music piece and says, here's some critique, and then the agents derive their own adaptation from this critic. This swarm here has no global feedback whatsoever. The agents in the swarm only talk to their neighbors. And the question is, can that lead to organized music? And in fact, it can. So I can show you their roles differentiate. We've quantified this numerically. And when you attach numerical values, you can actually show local equilibria. You can look at the change of the traits, and you can associate them with global maxima in the performance to the objective. You can synthesize audio from this, and obviously I don't have time to talk about this, but the paper will be posted in arXiv very soon. You can then analyze the audio. So the question is, what is better? Of course, you can listen to it. I didn't have time. You can listen. I'll post it on SoundCloud when it's done. I can play it now, but maybe we're out of time. But you can also use math to analyze it. So we did some spectrograms. We did some.
Just play us a little
bit. A little bit easy. Oh yeah, sure. I mean, as I play you, this is the swarm. I don't know if you can hear it. Can you hear it? There's nothing. Yeah, I think it's because the. Let me see. I had to turn off the audio because of because of Zoom. Yeah, it creates some feedback. Anyway, but maybe you can look at the math analysis. It's even better. Because so no, we were done. But basically, you can analyze it, and I'll end with this, and you can show that in fact the swarm has a much more sophisticated musical structure than the single shot composition, which is basically taking a sort of specialized music algorithm, or the traditional swarm with global. So the self-organization is really, really powerful and leads to some really interesting features. Okay, with that, thank you so much. And I will, thank you for giving me a little more time.